Hello, today we're continuing in our series on GCSE physics revision, looking at alternating current, the national grid and domestic electricity. So essentially we're looking at how electricity is generated, how it's transmitted and how it is distributed to our homes. We've already seen, of course, how a generator can in principle produce electricity. But how is this worked in a power station? A power station basically has three elements. The first element is the fuel. That might be coal or oil or even nuclear fuel. In the case of coal and oil, you burn it to produce heat. In the case of nuclear fuel, the nuclear reaction itself produces heat, and that heat is transferred to the second part of the power station, which is the turbine. The turbine is a device which will produce, as it were, rotating energy from heat energy. So the heat comes in, it may be the hot air rises, it turns paddles, which effectively turns a turning wheel. That's how you get the turning part, which is then forwarded to the generator, and the generator is what we've seen before, the coil of wire in a magnet, or maybe a magnet in a coil of wire, but either the coil or the magnet are rotated by the turning power generated from the turbine, and that of course produces the electricity supply. A lot of electricity of course is now produced by wind power. Wind is of course, if you like, the fuel, but you don't need a turbine because you are not essentially burning energy or burning fuel to produce heat energy. The wind power goes straight to the generator, so the wind power is turning the coil directly because it's turning the windmill, and that turns the coil or the magnet, and that generates the electricity directly. There are many power stations and they all contribute their electricity to what is called the national grid, which is a distribution network which takes electricity from the power station and delivers it to homes and factories and so on. In the UK, the domestic electricity supply is 230 volts and the frequency is 50 hertz, which means that the coil in the generator is essentially rotating 50 times, complete rotation 50 times per second, and is thus producing an alternating current where you get essentially 50 complete waves per second. So the way it works is that there are many power stations which may be coal or oil or nuclear or wind. They all count as power stations, and they're all contributing their electricity to the national grid. They all have to be, of course, all that power has to be transmitted, and there are two main ways that that happens, either through pylons going across country, so the electricity is sent across pylons across miles and miles of countryside, or of course it can be buried underground, but that's more expensive. And then eventually it gets to a satellite station, which is, as it were, is a local distributor of power, and then that goes out to each of our houses so that we get domestic electricity at 230 volts and 50 hertz. Although the domestic supply is 230 volts, it is likely to be transmitted over the cables of the order of 40,000 volts. Why is it so high? Well, it's all to do with minimising the power loss in the cable itself. Now, power, you remember, was voltage times current, and Ohm's law says that V equals IR. So if we substitute this V here for IR, you get that the power is equal to I times IR, which is I squared R. So the higher the current, the higher the power loss. So in these cables, which go across the pylons, there will be a resistance. Now you might think you would use a good conductor, and indeed they do. You'll recall that when we spoke about resistance, we said that the resistance of a wire is made up of three things. The resistivity of the wire, which is a feature of the actual element that you use. Copper, for example, has a very low resistivity, so it contributes very little to the resistance. It was divided by the cross-sectional area, so the bigger the cross-sectional area, the smaller the resistance. But it also depends on the length. This, of course, is the cross-sectional area. This is the length. Now, for the cables which take electricity along the pylons, almost certainly they will use copper wire, so that will have a low resistivity. They will have as thick a cross-sectional area as they can, but there's a limit to how thick you can make this cable, because the thicker you make it, the heavier it becomes, and the more difficult it is to make sure that it doesn't break or sag or fall off of the pylons. But the thing you can't change is the fact that the length of those cables is likely to be many, many miles as the electricity is transported across the countries. So there will be a resistance in this cable, even though it is almost certainly a copper cable that's very thick, to minimise the cross-sectional resistance. But the length just means that there will be a resistance. That resistance you can't do anything about. But if you can make the current as small as possible, then the power loss just in the cable, which of course will be in the form of heat, the cables get hot, the power loss will be minimised if I is low. And going back to this equation here, power is voltage times current. For any given power, if you want the current to be low, then the voltage must be high. As the current falls, the voltage increases for any given power. So consequently, if you push the voltage up to 40,000 volts, the current that's flowing will be very small, and therefore the power loss will be very small. So in order to do this, we need to have transformers between the power station and the electricity national grid. These will be step-up transformers, so you take the voltage up to 40,000 volts, and then when it gets into the distribution station, there will be a step-down transformer which steps from 40,000 volts to 230 volts, and that is the supply that is fed to your homes. In essence, therefore, power stations are means of taking one form of energy and converting it into electrical energy. If it's coal or oil, then you're using that fossil fuel to create heat, to drive the turbines, to drive the generators to create electricity. If it's nuclear fuel, you're using the nuclear reaction to create heat, to drive the turbine, to drive the generator. If you're using wind energy, then you're using the wind directly to turn the generator. And similarly, if you use water energy, you can have a water wheel. Similarly, that too is just spinning and turning the generator. The people who operate the national grid need to be able to respond to changes in demand quickly. For example, suppose all these houses are watching a very popular television programme, and that may be on a commercial station. When it gets to an intermission, when the commercials come on, the advertising break, many of these people may go out and make themselves a cup of tea. That involves putting the electric kettle on, and there's suddenly a very strong surge in demand during the commercial break. And that means that the people who are running the national grid have got to suddenly produce a lot more power. So what they will do is they'll have a power station standing by, and as soon as that power demand increases, they can bring another power station on stream to contribute additional power where it's needed. Similarly, when the commercial break is over and the programme restarts and everybody's sitting down drinking their tea and there's a much smaller demand, then some of these power stations can be, as it were, taken offline. They're still operating, but they're not contributing power to the national grid because there's no demand. And finally, for this little section, we need to recognise that power stations are not particularly efficient. The definition of efficiency, in terms of at least what we want here, is that the electrical output energy, so electrical output energy divided by the total input energy, must be as high as possible, because that means you've used as much of the input energy, whether that's heat or nuclear energy or wind energy or whatever, to convert into electrical energy. And ideally you want that to be as high as possible, but it's always less than 100%. In other words, when you heat the coal, or you burn the coal, burn the oil, that produces heat. By no means all of that heat goes into producing electricity. A lot of it is wasted and lost. So the conversion of other forms of energy to electrical energy is not 100% efficient. So the next stage is bringing that electricity into your home. And as we've already said, if you plot voltage against time, what you get is an alternating voltage, which produces an alternating current. One complete wavelength, or one cycle, will, 50 of them will travel past a fixed point in 1 second. That's called the frequency, and the frequency, as we've said, is 50 Hertz. And the voltage is 230 volts, and you might think, as I said in a previous video, that that would be the maximum voltage, but of course that is not true. The 230 volts is, as it were, a weighted average, so 230 volts is probably something like that. It's not the absolute average, of course, because the absolute average voltage is 0, because there's a positive half here and a negative half here in one complete wave, and the two would cancel out. So the average is strictly 0, but the weighted average, which is called the root mean square, sits somewhere along here, and the actual peak is over 400 volts in a domestic supply. But of course you only get over 400 volts for a small fraction of each cycle. So the kind of weighted average you get, which is just the accumulation of all of this, comes to 230 volts. If you contrast that with, say, a 9-volt battery, and we were to plot voltage against time, then the 9-volt battery would simply produce 9 volts until such time as the battery ran out of power. There is no variation, it's just a straight 9 volts. Now I said that the frequency of the alternating current is, or alternating voltage, is 50 Hertz, 50 cycles per second. And as we've seen before, there is a formula that relates the period to the frequency. The period is 1 over f, and the period is the time it takes for just one wave to pass a particular point. So these waves are travelling in this direction, and when one cycle moves past a fixed point, that's called the period, the amount of time it takes for just one wave. The frequency is the number of waves per second. The period is the time taken for one wave to pass a particular point, and they are related by t is 1 over f. So if the frequency is 50 Hertz, then t is 1 over 50, which is 0.02 seconds. So in other words, one wave passes a particular point, or one cycle passes a particular point, every 0.02 seconds. In the UK, there are 230 volt sockets in the wall, and they are the source of the supply, and in order to attach an appliance to them, we plug them in using a standard 3-pin plug. And if you open a 3-pin plug, which you should never do if it is connected to the main, so always make sure it's disconnected. If you open a 3-pin plug, you'll find that there is a thick cable coming in, but within that thick cable, which always has a plastic surround, there will be 3 other cables, also with plastic surrounds. The first of them will be green and yellow, and that will go to the, well, let's just mark it, this is green, yellow, and that goes to what is called the earth connection. So that's the earth pin of the 3-pin socket. There will be a blue cable, a separate blue cable, which goes to what's called the neutral pin. And there will be a brown cable which doesn't go to a pin at all. It's brown, and it simply gets screwed into a connector here. The actual pin is here, and between the two there will be a fuse. So the idea is that the current comes in through the pin, goes through the fuse, and then goes to your appliance, whatever that appliance might be. But if something goes wrong and the current increases, then the fuse will burn out, and when it burns out, that will effectively disconnect the current. So it's a safety device. And we discussed this before with fuses. The idea of a fuse is that it has a very thin piece of wire in the fuse, and the power across that fuse will be I squared R, just as the power across the cable going between the pylons was I squared R. And if power increases, if I increases, the total power increases, this wire will get hot, it will melt, and consequently it will break the circuit. So that's the mechanism for the safety device. But remember this, it's an alternating current. So in other words, the current is at some point going through the brown cable and sometimes going through the blue cable. So even if the fuse burns out, there's still a possibility for the what we call the neutral cable to give you an electric shock. So don't think that the neutral cable is entirely safe if the brown cable is disconnected. There can still be danger in the blue cable. The general rule is, when the plug is in the socket in the wall, do not interfere with any of the cables. The way the earth wire works is that if you've got an appliance which has a metal exterior, so it's something that you could touch, is metal, then that will be connected to what's called an earth wire, which will go in through the earth pin, and then the green and yellow cable goes all the way down into your supply, and in fact goes through your home and is buried as a big copper cable underneath your house in the earth. So the idea is that if the metal casement of any of your appliances were to become live because something went wrong, such that if you touched it you would get a very nasty shock, the electrons which are now on that outer metal case will instead flow through the earth wire, down the green and yellow cable and down to earth. Again, it's another safety device to ensure that should any external metal frame of your appliance become live, the earth wire protects you. A number of appliances, of course, don't have any metal in the exterior. My hairdryer, for example, is plastic. Plastic is an insulator. So effectively, you don't need to earth a plastic container because it is already resistant to any electricity flowing through it. But if there are any metal bits externally, they have to be earthed. And of course the manufacturers ensure that that's the case. When you wire the plug, what you are effectively doing is connecting the green-yellow cable which goes down to earth to the cable which the manufacturers will provide that attaches to the outer casing or the outer metal casing of your appliance. Fuses in the UK are generally rated at 2 amps, 3 amps, 5 amps and 13 amps. And the idea is that you want a fuse which is just slightly greater than the normal operating current of the appliance you're using. So if your normal operating appliance operates at, say, 2.5 amps, then you want a 3 amp fuse, because if the current gets to 3 amps, that means something's gone wrong, because the normal rating would be 2.5 amps. So if there's a current of 3 amps, something's gone wrong, you want the fuse to blow. You wouldn't put a 2 amp fuse in because the normal operating current is 2.5 amps and that will blow a 2 amp fuse, so that's a waste of time. Nor should you have a 13 amp fuse. This is a common mistake. People think that all plugs are 13 amp plugs. They are not. They are whatever fuse you put in. If you normally have a current of, say, 2.5 amps, you should have a 3 amp fuse, not a 13 amp fuse. Because if you have a 13 amp fuse for something that is normally rated at 2.5 amps, you've got to have a massive increase in current before that fuse will blow. So you could have something wrong with the device and still the fuse doesn't go because the current hasn't yet reached 13 amps. There are now devices on the market called circuit breakers or residual circuit breakers, which have the advantage that instead of having fuses that blow, they simply have switches that switch off and that can be reset. The advantage, of course, is that if the fuse goes, you've got to replace it. If the circuit breaker flips off, then all you've got to do is to switch it back on again. A number of fuse boxes in where the electricity supply comes into your house are now of the residual circuit breaker type, that if something goes wrong, the switch immediately switches off. That cuts the current to that particular circuit in the house. But once you've satisfied yourself that you've put things right, you can simply flip the switch back up again and the electricity comes on. Generally speaking, the way that this works is that, of course, as we've said, there's the brown wire, which is the live wire, and the blue wire, which is the neutral wire, and alternating current is, of course, flowing backwards and forwards through these two wires. And what the residual circuit breaker is capable of doing is checking the difference between the levels of the current that is flowing. Ordinarily, if everything is going right, there shouldn't be any difference because this is just the same current alternating between the two wires. But suppose something goes wrong and some of the current in the brown wire starts leaking out through you, because let's say something's gone wrong and now the appliance has become live and there's a risk that some of the current will flow out and do you damage. The residual circuit breaker detects that there is a difference in the current in this wire and this wire, and it can detect very, very small differences, and it immediately shuts off the current, and that is keeping you safe. Of course, it is detecting very, very small differences because any small difference could have a major effect on you, so it needs to shut down quickly. But it does, of course, mean that every so often, if there is a kind of an electrical surge in your power supply, you may find that the residual circuit breaker will flip off when in fact there was nothing wrong. And that can be a bit frustrating, but rather that than that you get electrocuted.